Okay, so last time we should have left off, we looked at what an exponential function was. We looked at all the properties of exponents. We did an example where we used the algebraic properties to solve an equation. We looked at the graphs of exponential functions, like they can increase or decrease. And then, if I remember correctly, we graphed two different functions, and we also looked at like just setting up a basic exponential equation of the form like a b to the x, right? So we talked about rates and how you can plug the rate in and out and how to deal with the base in a word problem. Hold on a second. You guys keep it down. Give it a mean face. All right, so if we want to, so let's just kind of recall from last time. This is where we kind of stopped. We said, well, the sort of most basic general form of an exponential equation, right, is this, right? Where A is going to be the y-intercept, B is the base, and X is in the exponent. And obviously, just like with anything we've worked within here, we can change X to T if we want to talk about time. We can change the variable to, the letter of the variable to correlate better with what variable we're talking about. So what I want to make sure that you guys kind of get down, the reason I want to emphasize this particular equation is we are going to look at lots of exponential equations, and they're going to look dramatically different when you first look at them, but they are all still of the form some constant up front times some b raised to an exponent. So that b may look like an expression, but it is still, if you type it in your calculator, you can collapse it down to one digit that is still 1 plus or minus r. It's a positive r if we're increasing, it's a negative rate if we're decreasing. So, all right, so what I wanted to do, is let's look at an application, all right? So this is a really common application. And this is an example where what I'm about to show you is in fact just a very fancy form of what we just looked at. All right, so one of the most common things we do with exponentials is we talk about interest and compound interest. So the formula that we use is the following. Where P is the principal, or that's another way of saying the initial amount. R is the rate, and it's the annual rate, right, in decimal form. N is going to be the number of times per year that the interest is compounded. And T is measured in years. So we can actually use this formula to figure out how much money we would have, right, at a certain time T based on how many times per year we compound our interest. So if the interest is compounded annually, well then N is 1 because it's just happening once a year, right? So one of the things you want to make sure that you're paying attention to on these problems is they're never just going to explicitly say N equals 3 or N equals 5. They're going to use words like annually, semi-annually, quarterly, monthly, right? So you have to know how many times per year that works out to be, all right? So if the most common ones you'll see is annually, right? That would mean N is 1, right? Semi-annually, right, N would be 2. We'll do one more. Quarterly, right, N is 4, right? And so then daily would be like 365, right? We just ignore leap year. We just go on a normal year. Weekly would be 52. So you don't want to lose points on a question over something silly because you don't know how many days are in a year, or you don't know how many months are in a year. So make sure that when you're looking at these problems, you get that down. All right, so let's look at an example. And just like always, right, you are always supposed to give an exact answer when, remember, and I mentioned this in class a bunch of times, but people didn't listen on the exam. If I do not tell you what to do with the decimal, in the instructions of the question, you are not allowed to have one. So a lot of people were giving me kind of decimal numbers and things like that. And even in some of the questions, give an exact answer. A decimal is not an exact answer. The only exception to where decimals are allowed to be used is like in these problems when we're talking about rates, because you have to convert a percentage into a decimal form to put it in the equation. But you'll see, we'll either ask you for an exact answer, and I'm going to show you what that means, or we will say round your answer to the nearest cent, because we're talking about money, so it makes sense, right? So you want to make sure that you're not doing any intermediary calculations on the calculator with these formulas. You have to learn how to type the whole equation in, because otherwise when you round, you're not going to get it to the exact penny, and you'll get it wrong. Yeah, question?
So if you don't say round in the question, and you don't say to use a decimal, does that mean we're supposed to get a whole number in our answer? Like,
It doesn't mean you'll get a whole number, it means you have to give me an exact answer. So 3/2 is an exact answer.
okay, so
1.5 is not. That is an approximation. Even though those two things are equivalent, the exact answer is 3/2, right? If you get the square root of 41, well, 41's prime, right? And then it's not going to have a square root, right? That is the exact answer. If you type that in your calculator, you're going to get a big, long decimal, because how do I know where to round it? How do I know what to do? So if the answer is 17/5, well, then 17/5 is the exact answer. So we're perfectly comfortable reading that. I also got a lot of mixed fractions on the exam, which was weird. I would get like 7 1/4 or like, 6 2/4. No one ever uses those, ever. So when you have like 7 1/4, well, that's not correct form. You would put it as one fraction. So, and it was really weird because somebody would have the fraction, convert it into a mixed fraction, and then go back, and it was just like a lot of extra work. I didn't really understand where that was coming from, but I had about a quarter of people do that, yeah.
You know how to change calculators to not do mixed fractions? Because mine takes me to a mixed fraction.
Are you using a TI 30?
Yeah.
Is it the one because the one I think we allow, I don't think should be interesting. Yeah, I can look in the,
1/2, like.
yeah, I can look in the settings and change that for you, but yeah, I didn't even realize those calculators did that. Yeah, they shouldn't. Okay, well then that explains it. Then if it's a calculator, people are getting off the calculator. So I was like, whoa, that's like really kind of complicated to do. So I don't understand why people are going to that. But yeah, we can change that in your calculator. But the issue still is you can't just type stuff in your calculator. You may have to, type the numerator, type the denominator, but we want exact answers. All right, so if you invest, let's say $1,500 into an account, oops, and APR stands for annual percentage rate, okay, so that's the annual percentage rate of, let's say, 3.2% compounded, let's do it quarterly, all right? And we want to know how much money let's say after 5 years. All right, and so what we're going to do is we're going to give an exact answer for part A, and then for part B, I'm going to have you round to the nearest cent. Okay? So, all right, so first thing we need to do is we need to make sure that we're setting everything up in our equation properly. So the amount of money in the account, right, we invested $1,500, so that's going to go inside the function. What the account is worth is the A value on the outside of the function. So we invested $1,500. Our rate is 3.2%. So they're always going to give you the percentages, right, or the rates in percent form, and you have to convert to decimal. So when we convert that to a decimal, that is 0.032, right? Compounding it quarterly means n is 4, and please don't forget there's another n in the exponent. So I'm going to plug in 4 times 5 in the exponent because it's n times t. So everybody always forgets about the n. All right, so what we have right now is the exact answer. You can just leave it. So So in this particular formula, there's not really a lot of simplification. You can't really simplify this much more, except you might put a 20 in the exponent instead of leaving it 4 times 5, but that's an exact answer. That's it. And I can see exactly that all the pieces are in the proper place, and I know that if I were to type this in a calculator, I would get the right answer. So that's what we mean by an exact answer. It's going to look like an expression sometimes when you're doing these equations. All right, so if we want to round this to the nearest cent, my calculator whip up. I want to show you how to type this into your calculator properly. So you're going to have a different screen than me, but I need this one so I can show you on the screen, but I'm going to type it in my calculator the way you can type it in yours, all right, just to show you the syntax. Okay, let me boot up. Okay. Let me see the screen. Yep, perfect. All right. So you want to type the exact expression. You don't want to don't do what's in the parentheses and then try to raise it and all that stuff. You want to do this all in one go so you get the right answer. So it's a 1,500 up front. You open the parentheses for what's inside the equation. It's a 1 plus, right? The rate was 0.032. Divide by 4 and then close the parentheses. And then what you want to be careful with is when you raise it, right, using a caret, well, you have two options here. If you know what 4 times 5 is and you just want to raise it to 20, you're fine. But sometimes you're going to have to like multiply things in the exponent. So you open parentheses for the exponent, 4 times 5, close parentheses. Because if I didn't put parentheses around the 4 times 5, it would raise everything to the 4, and then the calculator would multiply the result by 5. So you want to put parentheses so it locks all of that stuff up in the exponent, right? And so then when I hit enter, we see we have $1,759.15 because I'm rounding to the nearest cent. And so you look to the number after the 4. If it's 5 or bigger, right, we go up. 4 or less, we go down. So right here, right, that's how I know that's 6, tells me to round that up to a 5. Okay? So this is going to be $1,759.15. So that's what we would have after 5 years in our account. That make sense? Okay. Now what's trickier, it's a little bit, this is pretty direct, right? You just plug everything into the formula and get the answer. What's a little trickier is when we say, well, when will the account have a certain amount of money? So if we want to solve for t, right, t is up in the exponent, we don't actually have any algebra tools technically yet that allow us to remove a variable from the exponent. All right, so we're going to have to look at, and this is why I think this is odd that they throw this at you. Maybe they're going to revisit this formula in the later section because you can't ask you all the algebraic questions we want to ask you because we haven't done logs yet, right, to get stuff out. All right, so one other thing I want to show you about this formula is I said that even though this looks really funky, it is still just a times b to the t, right? And so let's deconstruct this equation for a second and show you what I mean. So the compound interest formula right, is this. But one of the things we learned with our properties of exponents was, who remembers what the rule is when you multiply exponents together? When you raise a power to another power, right? So we said if we had x squared and we then cubed it, you multiply the exponents together. So what's happening here is this could have been n raised to the t and someone combined it and multiplied them together, or it could have been t raised to the n, okay? But since the variable in question here is time, right, we can rewrite this the following way. So I argue here is A, this whole thing is B, and it is still of the form A times B to the T, or A times B to the X. So if we wanted to look at the problem we had, and I wanted to know what this base was, right, I could simply say, well, B is 1 plus 0.032 over 4 raised to the 4 for this particular question. And that would give me something along these lines. And I'm going to take it out several places so we can see what's happening here. All right, so I'm just going to go out a ridiculous long number of decimal places. So the annual rate for this account was 3.2%. So that means if I only charge interest once a year, right, I just take 3.2% of whatever's in the account. But when you compound the interest in times of year, what's happening is when you do it quarterly, for example, at the end of the first quarter, you're getting a quarter of the total rate. So if we take 3.2%, right, that's nice, that's divisible by 4. So we're getting 0.8% every quarter of our interest rate. And then you add up 0.8, 0.8, 0.8, 0.8, it's 3.2, okay? So at the end of the first quarter, they take the $1,500 we invested and they multiply it times 0.8, and they give us our first interest payment. So now we have a little bit more than $1,500 in the account, right? And then at the end of the second quarter, they multiply by 0.8 again, but it's not just the original $1,500, right? It's on the $1,500 plus we get to earn interest on the interest we got from the first quarter. And then that happens again in the third quarter and the fourth quarter. So the number of times a year you're compounding the interest, you're creating more opportunities to earn money off money you've already earned that year. So the more times a year you compound an interest account, the more money you'll have in the account at the end of the year than as if you just did it one time. So what this B is, when you put the equation back in this absolutely most basic form, is this is giving you essentially what we call the effective yield rate. Meaning the annual rate was 3.2%, but we said that B, right, is 1 plus the rate. So I can write this number as 1 plus, right, 0.032, and I'm just going to take it out to the 6 this time, right? And then if that's the rate, well, that actually works out to be 3.281%. So this is what's known as the effective rate. And so what we mean by the effective rate is on December 31st, let's imagine we deposited this January 1st, we did our 4 quarterly interest payments. On December 31st, your total interest for the year was 3.281% of the $1,500 you put in. If we had only compounded annually, then we would have only earned a flat 3.2. Where did the 0.081 come from? Well, that's the extra interest you earned on the interest you had previously earned when we kind of compounded out, right? So there's a fun example that I like to do that kind of illustrates this a little bit better, right? And does anybody in here know what the Buffett rule is?
Jimmy Buffett?
Not Jimmy Buffett, Warren Buffett, but close. That'd be the margarita rule. So the Buffett rule is, it's not an official policy, but Warren Buffett, who's super, super, super rich, very close to being the richest man on the planet, from Omaha, he made the statement publicly that my secretary shouldn't pay higher taxes than me, right? He's billionaire. She probably gets paid pretty well, but nowhere near on his level. Definitely not a millionaire. And what he meant was, of course Warren Buffett pays more in taxes every year than his secretary does. What he's referring to is the effective rate, okay? So when you're really, really, really wealthy and you have a lot of property and you own a lot of possessions and you can hire very good tax attorneys, you actually have way more opportunity to come up with deductions and reduce your tax bill, right? But when you don't own a lot and you don't have deductions you can make and you can't itemize, you just kind of have to pay the rate that you're assigned by the government. So if we were to look at something like this, all right? Let's say that you make $25,000 a year. And your tax rate on that money, and we're going to say it's 25%, so just make some nice round numbers. If you don't have any deductions, like you don't have a house you can deduct the mortgage on, you don't have whatever, but let's just say at the end of the year, this was the amount of taxable income you had. Well, if you had to pay all $25,000 on that money, right, your tax bill would be $6,250, and your tax rate would equal your effective rate because you didn't have any, it's just the same. They just charged you the $25,000, right? But then let's say you bring home $100,000 a year, right? And your tax rate, we have a graduated tax rate, so let's just say that you're supposed to pay 30% of your total income, which means you should have a tax bill of $30,000. But you own a house, you have a car, you've got maybe a couple kids, you know, I mean, you've got some deductions. And after you make all your deductions, you're now down to about $70,000 in taxable income. So then you're taxed at your 30% rate. And so you pay $21,000 in taxes. It's a lot, but let's just say that's what happens. So your effective rate is not 30%, because 30% of the $100,000 would have been like $33,333, right? Or it actually would have been $30,000. You paid $9,000 less in taxes because of your deductions than you should have paid under the bracket you were in. So to get your effective rate, right, there's two ways you can do this. You can take the amount of money you paid in taxes, right, and you can divide it by what you actually made. And this is 0.21, so your effective rate was only 21%. So you saved yourself 9 points, right? And so what Warren Buffett was alluding to is when you have billions of dollars, right, you can whittle your deductions around and you can invest things in certain ways where they're taxed at the lowest possible rate. Some things have no gains. You can roll stuff over into the next year. You can take a loss on, you know, and depreciation on things you have. So you can literally get an effective tax rate of down to like 9%. And that's what he meant. So his secretary's probably paying in the 20s. And he's paying 9%. Now, 9% of millions of dollars is still millions of dollars, right? But in some instances, we were talking about hundreds of millions of dollars. And she's probably paying thousands of dollars in taxes, but the hit to her income is much, much bigger than the hit to his. And so that is what the effective rate is. What would the rate be if I just look at the end result at the end of the year and we said, okay, well, if I only did it once, that would be the rate. So if we only slapped you once with this bill, it'd be 21%, right? Even though it was supposed to be at 30%. So what you'll see with investment accounts, which is what we're going to do a lot of stuff with when we're doing bank accounts and investments, the effective rate should be higher because we're earning more money, right? In a tax situation, the effective rate, you want it to be lower because you want to save money, okay? So let's look at a fun problem I like to do. So let's say that you take $1. And if you are going to take calculus, save this problem we're about to do, because we're about to define something that will be very important to you later. And I was actually very proud of my pre-calc students when they took my Calc 2 class. They actually remembered this example. So, because it's an equation that nobody remembers, and I'm going to show you where it comes from. All right, so P equals 1, right? $1. And let's say that you find some really silly investor who finds you an account that's going to pay you 100% interest rate. Sure thing. Meaning, you put $1 in January You let it ride to December, you're guaranteed $1 at the end of the year in interest, okay? And we're gonna look at this at the end of 1 year. And what we're gonna play with in this problem is how many times we compound our interest, all right? So our formula, we'd have $1 up front, right? 1 plus, and 100% when converted into decimal form is a rate of 1. And we have n, because we still don't know how many times we're going to compound it yet, times 1 year. So this just works out to be 1 plus 1 over n to the n. And this is a very famous mathematical expression. All right, so let's see what happens if we look at the different times we compound. So if n equals 1, sorry, I'm going to cheat for a second so I can find these numbers quick. So when n equals 1, oops, you should have $2 at the end of the year because you have the dollar you started with and 100% of $1 is $1. So you would have $2 in the account. At the end of the year, you would double your money. All right. If n equals 2, well, then what happens is at the end of the first 6 months, right? We're going to give you your interest every 6 months. So at the end of the first 6 months, we're going to pay you half of the interest we owe you. And it's not we're just going to pay you 50 cents. That's not how that works. They don't come up with the dollar amount and divide it that way. They divide the interest rate. So they say, we're going to give you the first 50% of your interest. So they'll do $1 times 50%. So you get 50 cents. Okay, so you have $1.50 in your account. But at the end of the year, they're going to go, okay, well now we're going to pay you the remaining 50%, but it's 50% of $1.50. So you would have $1.50 in your account after the first 6 months, right? Then you would get another 75 cents in interest, right, on the second amount, and you would end up at the end of the year with $2.25. Oops. Make sure I do this right. Sorry. I wanted to write it like this. You have your dollar, right? Plus you get 50 cents after 6 months, plus you get another 75 cents right at the end of a year. And so the total amount you end the year with is $2.25. So just by compounding the interest one additional time in this scenario, you made 25 more cents in the end of the year. Okay, so that's a pretty, you start multiplying that by multiple dollars, that's a pretty big jump, right? What happens if we do it quarterly? So if we compound it quarterly, well, at the end of the year, we have $2.44. So I'm not going to break them all down into each individual payment. This is just an easy one to see why. Does everybody see why you're getting a little bit more money each time? Because you're earning money on the interest you earned on the previous payment, right? So then the next logical thing would be, well, if we do it quarterly, right, let's do it monthly. So let's say we pay your interest every month. Oops. Stop. Stupid calculator. I don't want to type this into this equation. It's annoying. There we go. So monthly, you would have $2.61. If we did it weekly, right, that's 52 times a year, you would have $2.69, all right? And then let's say we do it every single day. Oops. I would have $2.71. Now, let's go nuts, and I'm going to say, well, let's say that I did it 10,000 times. So that would give me 1 plus 1 divided by 10,000 raised to the 10,000. And I would have $2.72 in the account. So what can you tell me about these numbers, other than they're going up? They're definitely increasing as we compound the interest, but what's happening about the way that they increase? Yeah, the gains are getting smaller, right? It's still going up, but it's getting smaller. And so if you were to graph these values on a graph, right, we would see, well, here's the amount of money, here's the number of times we're compounding it. They sort of seem to be capping out, right? Because look what happened. You went from 365 times compounding to 10,000 times compounding, and you only gained a penny for doing that, right? So I would say we're kind of hitting the upper limit of what we can make here on this account, right? So if you look at $2.72, right? This looks something like this. So we started with $1, and the amount of money is doing something like that. It is increasing, right? But it's decreasing as it increases, and so it's going to cap out. So does anybody recognize or have any idea what the number 2.72 might be? It's an asymptote, but I mean the actual number. Does anybody recognize that number? Or 2.712? Nobody? Okay, that's cool. It's all right if you don't. So, it is the natural number. Some of you may have learned in school. All right, that's as far as my calculator will show me. Oops. So E is the natural number. Just like pi, it is an irrational number, meaning its decimal places go on infinitely long forever, right? You always have those contests where you have those nerds that want to memorize like hundreds of digits of pi, right? So E is a number, it's an irrational number. And what we're seeing is that if you start with $1, right, and this $100 or 100% interest rate, the expression we came up with of 1 plus 1 over n all raised to the n is actually the mathematical definition of E, right? And so E is equal, and this is e to the 1, is equal to 1 plus 1 over n to the n as n goes to infinity. So if you just make n ridiculously huge, then that expression will basically work out to be E, and you'll see the same digits. So if, let me move this down real quick. So if you look on the calculator here, here's where I type 1 over 1 to the 10,000 raised to the 10,000, and look what I got. If you just tell your calculator to give you E, look how close they are, right? And so if I had gone to like 200,000 or 400,000 or 1,000,000, right, I would have just gotten closer and closer and closer to that value E. So that asymptote on that graph is in fact E, right? So E is quite useful. So we actually can have a exponential function e to the x. So now when you see that letter E, know it's just a number, right? It's not an electron. And the value of it is, right, approximately lost my paper, here we go. 2.718, right? We never, ever, ever use the decimal number, right? But you need to know the value of it because you need to make sure you understand E is greater than 1, but e is less than 3. So it's somewhere between, right, 2 and 3. But the fact that it's greater than 1 means what type of exponential function is this? It's growing. So just like the general graph we did last week of b to the x, well, we know y equals e to the x is going to look like this because the base is e and e is greater than 1. It still crosses the y-axis at 0, 1 because the y-intercept is 0, 1. E is a one-to-one function, so it's invertible, just like all a to the x's when they're growing, right, are going to be invertible. And we said that if we want to graph an inverse, right, that's what we kind of did back at the beginning of the unit, we said, well, the inverse is just reflected over the line y equals x, and it's switching its x and y values. So the inverse of this function is going to look like this, and instead of crossing the y-axis at 0, 1, it's going to cross the x-axis at 1, 0. And the equation for the inverse of e to the x is natural log of x, and that's where we'll want to pick up, and we'll also have a couple more minutes. We'll talk about natural log for a second. So what is the natural log of x, right? And more generally, what we would say is if I take any graph b to the x, right? This is for an increasing where b is greater than 1. These graphs also have inverses. And we would say its inverse is log base b of x. So the structure of a log equation is just like we said with the exponential equation, right? We had a base, the variable was in the exponent. With logs, they also have a base. And when you're comparing a log to its inverse, which is an exponential function, they're inverses of each other, right? The base of the log has to match the base of the exponential. So you can always take an exponential function and turn it into a logarithmic expression and vice versa. And so my favorite example of how to remember how to do this is the following. So this is the base, right here. This is read log base 2 of 32, because it's a function, so we say of, right? We're talking about a function, is 5, right? And this is my favorite, personal favorite, because 2 and 32 and 5 are nothing alike numerically, but it's almost impossible to mess up their relationship. So if I wanted to write an equation just using 2, 5, and 32, what would I probably have to say? How are 2, 5, and 32 related? Right, so think about it. We're talking about exponentials, right? 2 to the 5th is 32. So the base, right, matches the base. And in the expression on the right, 5 goes into the function and 32 comes out. On the expression on the left, 32 goes into the function and 5 comes out. They are inverses, so their x's and y's are switched. Okay? And so what this is going to do is this is going to set up some new box of algebra properties we have to work with these functions back and forth so we can then solve them. So the punchline for today is that that logs and exponentials are inverses of each other. And we're going to get into logs a little bit deeper. That's going to be part of our Monday lecture. And then also you want to make sure that you practice working with these compound interest formula. That's an exponential function, and I want you to make sure you understand that those still fit that standard definition. All right, so before